Hey there. You ever feel like you're just trying to keep up with all the huge ideas flying around about the universe?
Oh, constantly. It's moving so fast.
Right. Well, today we're grabbing onto one that's genuinely like mind-bending. It could seriously shake up how we understand everything.
Absolutely. We're diving into an idea that connects back to Stephen Hawking himself.
Exactly. We're using Sabine Hossenfelder's recent article, Has Stephen Hawking's black hole theory just been proven? As our guide.
And that title really sets the stage, doesn't it? It's a big question.
Hmm.
So our mission today is to unpack this. What is Hawking's theory, really? Why is this one particular signal, this neutrino, causing such a stir?
And yet, what could it all mean if there is a connection? Let's try and get to the bottom of it.
Okay, let's start with the basics. Black holes, we think of them as cosmic vacuum cleaners, right? Point of no return.
Totally. Nothing gets out.
Yeah.
Or so we thought. Because Hawking, back in the 70s, he had this pretty radical idea.
He did. He kind of turned things on their head by bringing quantum mechanics into the picture near the event horizon.
Right, that edge. Yeah, the edge. He theorized that because of these quantum effects, black holes aren't perfectly black. They should actually leak particles, a very faint stream.
Leak. So they're not just taking, they're giving something back, like a slow exhale.
That's a great way to put it. This leakage is what we call Hawking radiation.
Wow. Okay, so if they're constantly losing this tiny bit of energy, this radiation, what happens to the black hole eventually?
Well, over incredibly long timescales, I mean, truly vast amounts of time, this loss of mass adds up. The theory predicts they should actually shrink and ultimately just evaporate completely.
And evaporate a whole black hole.
Okay,
But the article says this radiation is super, super faint for the big black holes we know about. Why so faint?
it's all about mass. The more massive the black hole, the colder it is, thermodynamically speaking.
Colder a black hole.
Yeah, in terms of Hawking radiation.
Yeah.
For supermassive ones, the radiation temperature is actually lower than the cosmic microwave background radiation, the leftover heat from the Big Bang. Ah, okay, so it's just drowned out by the background noise of the universe, basically.
Exactly. Detecting it directly from a big one is, well, likely impossible with current tech.
Okay, so if the big ones are too quiet, what about these primordial black holes mentioned in the article? What's the deal with them?
Right, so these are hypotheticals. The idea is they might have formed right after the Big Bang when the universe was incredibly dense.
Not from collapsing stars, but from the universe itself sort of squishing.
Kind of, yeah. And critically, they could be much, much smaller than the ones formed from stars.
And smaller means.
Smaller means hotter in terms of Hawking radiation, much more intense, potentially intense enough that we could detect their final evaporation burst.
Okay, that makes sense. And isn't there also a link to dark matter?
Yes, that's another fascinating angle. For decades, these primordial black holes, or PBHs, have been candidates for explaining dark matter, the universe's missing mass.
So finding them evaporating could solve two massive mysteries at once. Dark matter and proving Hawking radiation.
That's the potential holy grail here, yes.
Mhm.
A two-for-one cosmic discovery.
Okay, my mind is officially blown already. Now let's get to the trigger for all this discussion, this record-breaking neutrino. What exactly did they find?
This is where it gets really exciting. Down in the Mediterranean Sea, there's this detector called KM3net. It's underwater.
Right?
And it detected a single neutrino, but the energy, it was off the charts. Somewhere between 100 and 200 peta-electron volts. PeV.
Peta. Okay, how big is that really? Give me some context.
Well, think about the previous record holder detected by IceCube in Antarctica. This new one is 10 times more energetic than that.
And 10 times.
And maybe even more striking, it's about 1,000 times more energy than particles get when smashed together in the Large Hadron Collider at CERN.
Whoa! Okay, so it's packing an unbelievable punch for a single tiny particle. Why is that specific energy range so important for the Hawking radiation idea?
Because it fits the profile. As these hypothetical small black holes evaporate, they get hotter and hotter, right?
Losing mass, getting hotter.
And as they get hotter, they emit particles with higher and higher energies. The models predict that in their very final moments, they should blast out particles, including neutrinos, in exactly this ultra-high energy range.
So it's like a final energetic gasp.
Precisely.
Yeah.
And neutrinos are perfect messengers for this. They're almost massless. They barely interact with anything.
Those particles, yeah.
Right. So they can travel across billions of light years, potentially from the very early universe, completely undisturbed, carrying that information straight to us.
So this single neutrino could literally be a signal flare from the death of a tiny black hole billions of years ago.
That is the tantalizing possibility, yes.
Yeah.
If this holds up, it could be the very first observational hint, direct evidence, really, that Hawking radiation is real.
Which would be monumental. I mean, confirming a theory from Hawking from, what, 50 years ago?
Exactly. It would be huge for fundamental physics, and it would also strongly suggest these primordial black holes actually exist.
Okay, but science means being skeptical, right? The article stresses caution. Are there any other known things out there in the cosmos that could possibly shoot out a neutrino with this much energy?
That's the million-dollar question, isn't it? And
Yeah.
right now, the answer seems to be no. Our standard astrophysical culprits, things like supernovae or the jets from supermassive black holes and active galaxies, they just don't seem capable of producing neutrinos at this extreme energy level.
So no known factories for these kinds of neutrinos.
Not that we know of, which makes the evaporating black hole hypothesis very compelling. But, it's still just one data point, one neutrino. We need more.
So how do scientists try and confirm it? If it's just one neutrino, how do you build a stronger case? What else would you look for?
Well, the key prediction is that evaporating black holes shouldn't just emit neutrinos. They should also emit photons, light particles, across a range of energies, including very high-energy gamma rays.
Okay, so look for the light that comes with the ghost particle?
Essentially, yes. The challenge is, photons interact a lot more with stuff as they travel through space. Gas, dust, magnetic fields. They can get scattered or absorbed.
Making them harder to trace back to the source compared to the slippery neutrino?
Exactly. It's much tougher. But if telescopes could detect even one high-energy photon coming from roughly the same direction in the sky around the same time.
That would be pretty convincing corroboration.
Oh, absolutely. That would significantly strengthen the case that we're seeing Hawking radiation from a primordial black hole. Scientists are definitely looking using gamma-ray telescopes.
Okay, fingers crossed they see something. So let's assume for a second this pans out. We find photons, the case gets stronger. What are the really big implications, especially for that dark matter puzzle?
It would be, frankly, revolutionary. If it turns out that dark matter is made up, at least in part, of these primordial black holes that are evaporating right now, that changes everything.
Yeah, so.
It connects cosmology, the study of the universe's structure and evolution, directly to particle physics in a way we haven't seen. It tells us something fundamental about what makes up most of the matter in the universe.
Right, and Hossenfelder gives this idea a credibility rating in the article.
She does, yeah. She puts it at a 6 out of 10, which, acknowledges it's a really strong possibility given what we know and the lack of alternatives.
But not a slam dunk yet.
Definitely not. A 6 out of 10 says it's a serious contender, maybe even the leading one right now, but we need to keep investigating other possibilities, however unlikely they seem. The scientific community will be scrutinizing this.
A healthy dose of excitement mixed with caution. It's still just amazing that we might be seeing a direct consequence of Hawking's purely theoretical work from decades ago.
It really is. It shows the power of theoretical physics to predict phenomena that we might only be able to observe much, much later. It's quite profound.
Okay, so let's quickly recap. Hawking said black holes aren't forever, they evaporate. We've spotted this neutrino with truly insane energy, way higher than anything else we know how to make astrophysically.
Uh-huh. And that energy matches what we'd expect from a tiny primordial black hole in its final moments.
And if we can find matching high-energy photons, that would seal the deal, potentially confirming Hawking radiation and giving us a huge clue about dark matter.
That's the essence of it. It's a super exciting time in physics.
It really makes you wonder, though. I mean, if these ancient black holes are real, and they're out there constantly fizzling out, releasing these fundamental particles, could studying more of these ultra-high energy neutrinos tell us something even deeper? Something beyond just black holes and dark matter? Like, are we maybe glimpsing some totally new physics about reality itself?
That's a fantastic question to ponder. It really pushes the boundaries, doesn't it? Every time we open a new window on the universe, especially with extreme phenomena like this, there's always the potential for discovering things we haven't even conceived of yet. It reminds us to keep looking, keep questioning.